All right, I've started to tee up that if we're going to calculate the area under the receiver operating characteristic curve, we're going to need to use integral calculus. But before we get to that integral calculus, let's learn how to create that curve itself. The creation of the receiver operating characteristic curve starts with an understanding of the confusion matrix. So this matrix isn't actually that confusing. All it is it's a table that tracks when a person or a model is confused, so when they make an incorrect prediction. So let's say that we are predicting whether an image is a hot dog or a not hot dog with our model. So in that case, there's two possible actual y's, correct y values. So 1 is where the image is truly a hot dog, and 0 is where the image really truly isn't a hot dog. Now, if our model predicts that an image that truly is a hot dog, then that's what we call a true positive. When it truly isn't a hot dog, and the model predicts that it isn't a hot dog, that's a true negative. Easy enough so far. All right, so what about when the model's wrong? Well, if it isn't really a hot dog, but our model predicts that it is, that's what we call a false positive. And if it truly is a hot dog, but our model does not predict that, then we call that a false negative. So now that we know this confusion matrix, let's look at some numbers and put these into practice. So let's say we have 4 hot dog predictions with our hot dog, not hot dog image classifier. Now, you might be wondering why there's a picture of a trilobite eating a hot dog here. And, well, I mean, it's here because we're talking about hot dogs, and also because this trilobite is the mascot of my book, Deep Learning Illustrated. So it's filled with trilobites, including, as it turns out, hot dog eating trilobites. So a little bit of an aside there, but let's talk about our model's predictions of whether an image is a hot dog or not. So we have 4 images that we test our model with, and 2 of those really are hot dogs, so we label them with a 1, and 2 of them are not hot dogs, so we label those images with a 0. Then we feed those 4 images into our model, and we see what its predictions are. So, for one of these images, it's very confident that it's a hot dog. It thinks there's a 90% chance that it's a hot dog. And for another one of the images, it's very confident that it isn't a hot dog. So it says there's only a 30% chance this is a hot dog, when it, in fact, isn't a hot dog. Well, but then it isn't quite as right about these other 2 instances. So let's go from these predictions of these 4 images and turn them into a receiver operating characteristic curve. So you get confronted here with a bit of a wall of text, but I'll walk you through all of it. So this is the information from the preceding slide. So we have our 4 images, and we have our model's 4 predictions as to what those images are. And what we do to calculate the receiver operating characteristic curve is we consider each of our model's prediction levels, except for the highest one, as the threshold for considering whether an image is a hot dog or not. So this expands greatly upon the relatively simplistic single 0.5 threshold that we would typically have for a simple binary classifier metric. So returning to our single threshold charts, we can see that this is relatively simplistic now, where we were only considering 0.5 to kind of arbitrarily be the threshold between 2 classes. Now, with the receiver operating characteristic, we consider all of the predictions except for 1 to be the threshold. And you'll see why we exclude 1. It just wouldn't make sense. We can cover all possible bases with just 3 of these. Now we're considering any different y hat value that our model has can be the threshold. And so the more predictions we have, the more thresholds we'll tend to have as well. All right, so let's start with the first threshold, with the 0.3 threshold. So what we do here is we say anything at 0.3 or below is considered to be not a hot dog by our model, and anything above 0.3 is considered to be a hot dog. So add that threshold this first image, which has the y hat of 0.3, is considered to not be a hot dog, while the other three images, because all of them have y hat values above 0.3, are considered to be hot dogs by the model. So most of these are correct classifications. Referring back to our confusion matrix table, the first image is correctly classified as a true negative, and two of the images above the 0.3 threshold are correctly classified as true. So these are true positives. But one of the images, which has a y hat above the 0.3 threshold, but is in fact not a hot dog, that is a false positive. Now, repeating that same logic at the 0.5 threshold, so our next y hat value, so we're now treating 0.5 as the threshold between whether the model considers something to be a hot dog or not. So anything at 0.5 or lower, it considers to not be a hot dog. Well, it's still right about that first image. It's still a true negative. Now our second image is being treated as not a hot dog, even though it is in fact a hot dog. So that's a false negative. And the other two images, which are above the threshold, are the same as they were at the 0.3 threshold. So one of them is a false positive, one of them is a true positive. And then finally, moving to our final threshold, 0.6, at this point, anything at 0.6 or lower is considered to be not a hot dog. And so our first two images, these are the same as they were before. One of them is correctly classified as a true negative. The other one is a false negative. And now we have our third image being treated as not a hot dog. It is in fact not a hot dog, and so it is now a true negative. And our true positive at 0.9 is still a true positive. So that's all of the work we need to do. Those are all the considerations we need to make at each of the thresholds. And now you can probably also see why we don't need to consider 0.9 to be a threshold, because we already have a tier where all but one of the images is considered to be not a hot dog. So there's no point in going to 0.9 here. All right, now that we have our counts of true positives, true negatives, false positive, false negatives, we can now, at each of the thresholds, calculate our true positive rate and our false positive rate. So let's do true positive rate first. So the true positive rate, we calculate that by taking true positives and dividing by the sum of true positives and false negatives. So let's count up our true positives. We have 2 of them at this threshold. And so we fill in 2 for TP in both the numerator and the denominator. And we also have Fn in the denominator, and there are no Fn's at this threshold, so that's a 0. 2 divided by 2 plus 0 is 2 divided by 2, which is equal to 1.0. At this threshold, we also calculate the false positive rate. So here we count up all the false positives, Fp, there's 1 of them. And so that shows up in the numerator and the denominator. And there's also 1 true negative. And so that gives us our formula for false positive rate at the 0.3 threshold. 1 divided by 2 is equal to 0.5. And we do the same thing at the 0.5 threshold and the 0.6 threshold. We calculate the true positive rate as well as the false positive rate. And you can confirm for yourself that these integers all line up with the formulas on the left. In the end, this big table leaves us with 3 coordinates that we can put on a chart of true positive rate versus false positive rate. By putting these 3 points on a chart, we can then have a curve. So once we've calculated the receiver operating characteristic, like we did on the preceding slide, we can plot all the points out on a curve. So at our 0.3 threshold, we have a point at a true positive rate of 1 and a false positive rate of 0.5. On our chart, that shows up here at a true positive rate of 1 and a false positive rate of 0.5. At our 0.5 threshold, we have a TPR and an FPR of both 0.5. So that shows up at this coordinate here, where TPR and FPR are both equal to 0.5. And then finally, for our 0.6 threshold, we have it located at a TPR of 0.5 and an FPR of 0. which on our chart is right here, TPR of 0.5 and an FPR of 0. We add 2 more points at 0, 0, and 1, 1, and then we link up the points into a curve. So this is our receiver operating characteristic curve. This allows us to compare the performance of various binary classifier models. In practice, we would typically have way more predictions, and so instead of this looking like a step, it would typically look more like a gentle curve. So here's my cartoon of how an ROC curve could look if you have many more data points involved. Effectively, if you end up with a curve that is right along the diagonal here, that is random performance. Your binary classifier in that case is performing just as well as chance. You might as well have a monkey picking whether images are hot dogs or not hot dogs. In fact, I bet you could train a monkey to do better than that. The better our model is at correctly predicting whether an image is a hot dog or not, the closer our curve will go to filling the entire square. So a model that performs above chance might have a gentle curve in toward the top left corner. A good model might start to press quite away towards the top left corner, and a perfect model fills up the entire space. So in this case, in order to get that perfect curve, for every positive case, so for every hot dog image, it would have to have 100% confidence that that is a hot dog, and for every image that is not a hot dog, it would have to have 100% confidence that it is not a hot dog, and so give it an output y hat of 0.0. And so now we have our receiver operating characteristic curve, and we know that the more of this square that it fills, the more area under the curve, the better the model is. So what we'd like to do is know exactly how much area of this square is under the curve relative to the amount that's above the curve. In order to calculate that, we can use integral calculus.